Then coming components of the cooling loads, and we have to divide some loads, that is the internal heat gains and the external heat gains also. In case of the internal heat gains, the sensible and the latent heat gain due to components that are lights, machines, piping, etc. within the conditional space from the components of the internal heat gain. The two main components of the cooling load imposed on air conditioning plant operating during hot weather are as follows. That is, one is the sensible heat gain and second one is the latent heat gain. Coming to sensible heat gain, when there is a direct addition of heat to the enclosed space, a gain in the sensible heat is said to occur. The sensible heat is removed during the process of summer air conditioning system. Then the latent heat gain, when there is an addition of water vapor to the air of the enclosed space, a gain in latent heat is said to occur. This latent heat to be removed during the process of summer air conditioning system. The latent heat gain may occur due to any one of or all of the following sources. They are heat gain due to moisture air in the outside air entering by infiltration. We discussed what is infiltration already. We have discussed previously also what is infiltration. And the second point is heat gain due to condensation of moisture from the occupants. Occupants means suppose if it is inside room, the human being is occupants. Depends upon their nature of work, it is heat we can calculate. Like natural work means they are simply listening in the class, or maybe they are doing many work in that, or maybe they are doing many computer work on that. These are called the occupants load. Then the third one is heat gain due to condensation of moisture from any process such as cooking food, which takes place within the conditioned space. That means suppose it is the kitchen room and some moisture from any process, maybe you can also consider for that also. The heat gain due to the moisture passing directly into this conditioned space through the permeable walls or partitions from the outside or from adjoining regions where the water vapor pressure is high. That means the walls, from the walls also, through the walls or through the partitions, also the heat may be transferred into the room. Then the total load, the total heat load to be removed by air conditioning and refrigeration equipment is the sum of sensible heat and the latent heat. That means the total load is equal to sensible heat plus the latent heat. Sensible heat gain through building structure by conduction. Conduction means already maybe you have studied the heat transfer, the modes of heat transfer. The modes of heat transfer, there are three types. One is conduction, convection and the radiation. In that, the walls, the heat gain through walls, through conduction, that is the heat gain through a building structure such as walls, floors, ceiling, doors and windows continues the major portion of sensible heat load. Consider a building wall composed of single homogeneous material. So in the next slide, that is figure number 19.1, a little consideration will show that the heat passing through a wall is first received at the wall surface, exposed to the region of higher air temperature by radiation, convection and conduction. That means there are three modes of heat transfer is there. It then flows through the material of the wall to the surface exposed at the region of lower air temperature. Now, the heat is dissipated and disappeared through the process of radiation, convection and conduction. Thus, the heat transferred or gained through a wall under steady state conditions is The formula that is the heat transfer rate, that is Q is equal to F naught into the temperature difference with the area and the K by X into the temperature difference and then the F5 into temperature difference to area. That is simply U is equal to UA into the temperature difference, that is the outside temperature and inside temperature, where the F naught is the outside film or surface conduction, and then Fi is the inside film or surface conductance, A is the outside area of the wall, and the figure shows the wall area, how the heat is transferred from TO. This is the TO, and then the heat is transferred to like this, and it is a T, this is the outside temperature, and this is the wall, and then this is the film, A, the air film. This is between a small gap with the air, and this is also a small gap, that is the film inside and outside. This is the outside film, that is FO, and this is the inside film Fi, and like that from outside temperature to the inside temperature. The wall starting temperature is T1, that is the outside inside air temperature, and the T naught, T out is outside temperature. The X is the thickness of the wall. This is the thickness of the wall, and the K is the thermal conductivity of the material of the wall. That means the wall, maybe it is a constructed by brick, or maybe any iron partition, or maybe wooden partition also, depending upon the material. The K may be changed. That is the thermal conductivity. Therefore, the U, that is overall heat transfer coefficient, and the overall coefficient of heat transfer of the wall is 1 by F naught plus X by thermal conductivity plus 1 by Fi. With this, you can calculate the heat transfer. When wall is made up of layers, different materials, as shown in figure 19.2, then the overall coefficient of heat transfer is given by. That means these are the composite walls. Sometimes maybe different materials. Heat transfer to a composite wall. That is K1, K2, K3. They are different materials. K1 is different, K2 is different, K3 is different. Like that, and this is a composite wall. And the figure 19.3 shows heat transfer to a composite wall with air space. Already have seen the first two diagram. This is the air space, and this is also air space, and this is also air space. So this is the composite wall, and finally we can calculate the overall coefficient of heat transfer with this formula. The type of walls are made for a cold storage with a maximum low temperature insulation of 10 cm. When air space is provided between the material, as shown in figure 19.3 previous figure, then the overall heat transfer coefficient is given by this formula, where K thermal conductivity of the air is here. In case of interior walls or partitions, floors and ceilings, the temperature is the adjoining unconditioned space is usually 5 to 10 degree below the outdoor temperature, outdoor design temperature. But for kitchens, boilers, boiler rooms, and then attics and doors, windows, it is often higher than the outdoor temperature. Because generally, the kitchen means somewhat temperature is more because we are using some stoves also for boiling or for cooking purpose. And the boiler also, boiler means automatically boiler means it is the generator, heat generator. That is the steam generation machine it is. We are getting the steam with the help of the boiler. That's why the boiler temperature is more. So the temperature of kitchen and the boiler are always be more than the outside temperature. The next one is the heat gain from the solar radiation. I think we know the solar radiation nowadays with the help of the solar, we are storing the energy also through the something that some plates with the solar plates, solar electric plates also are using. And now the solar radiation striking the outside surface of the building may contribute the peak load on the air conditioning and refrigeration equipment and must consider the amount of heat flow, the amount of heat that flows towards the interior of building due to depends upon the following factors. Altitude, angle of the sun, that means the sun is some inclination, maybe and then maybe midday, that is afternoon. Generally at 2 o'clock the temperature is higher compared to the other timings. The second one is the cleanness of the sky. If the sky is very clean, that means the clouds may be not there, then also the temperature is more. And the position of the surface with respect to the direction of the sun rays. Then the fourth one is the absorptivity of the surface. And the fifth one is the ratio of the overall coefficient of the heat transfer of the wall to the coefficient of heat transfer to the outside air film. And the sixth point is the temperature of the ground and surrounding objects with which the heated surface may exchange radiant heat. The altitude, the angle of the sun in turn depends upon the activity of the locality also. The heat from the solar radiation is received by building surface in two forms, that is direct radiation and sky or diffuse radiation. The direct radiation is the impingement of the sun rays upon the surface. The sky or diffuse radiation is received from the moisture and dust particles in the atmosphere which absorb the part of the energy of the sun rays, thereby becoming heated to a temperature above the top air. The sky radiation is received by surfaces which do not face the sun. Then the solar heat gain or sensible heat gain through the outside wall and roof. The transfer of heat through the walls exposed to the outdoor and roof is not steady due to variation of the outside air temperature and the solar radiation intensity over the period of 24 hours. A little consideration will show that the temperature of wall rises with the rise in outside air temperature and the heat is stored in the wall, which was a considerable storage capacity. Thus, the heat transferred to the roof is reduced. The stored heat in the wall is given off to the room when the outside air temperature falls. Since the outside temperature of air changes continuously over a cycle of 24 hours, therefore, instantaneous heat gain from the outside air is not equal to the instantaneous heat gain inside the room. The difference being stored or presented by the wall. The heat stored by the wall is given out later in the evening. See the diagram here. This is 6 a.m. in the morning, and then the 10 a.m., then 2 p.m., and then 6 p.m., 10 p.m., 2 a.m. early morning, and 4 a.m. These are the temperatures. You see that at 2 o'clock or maybe 3 o'clock, the temperature is maximum. The y-axis is the temperature, and the x-axis is the time. See, hours instantaneously. This is this line is the instantaneous load from the outside and the actual load inside room. This is the inside room. So you see the maximum temperature, it can be at after 2 p.m. and between 3 or 4 p.m. here. Thus the peak of incoming heat rate is delayed by the storage effect of the wall, and it is also reduced. The figure shows the current instantaneous load coming from the outside and the actual load inside. The area under the two curves is equal. The shaded area above the actual load shows the heat stored, and below the actual load shows the heat released by the walls and other structures. convenient method of taking into account this lagging effect of storage in the solar radiation is to use an equivalent temperature differential. The equivalent temperature differential for rooms are given in table 19.6 for the table, and those applying to walls is given in table 19.7. The heat gain through outside walls and rooms is given by the formula, that is general formula, it is Q is equal to the overall heat transfer coefficient U and area and the temperature difference, where the U is the overall heat transfer coefficient of the roof R wall and A is the area of the wall R roof, and equivalent temperature differential, this T is. Then the solar air temperature, it is hypothetical temperature used to calculate the heat received by the outside surface of the building wall by combined effect of convection and radiation. The heat received by the outside surface of the wall by convection is given by, this is the Q is equal to F naught into the temperature difference, where the F naught is outside film coefficient and T naught is the temperature outside air, T AS is the temperature of the outside surface of the wall. This is the figure, this is the outside surface, and this is the wall, and this is the inside space. This is the solar air temperature. The heat received by the outside surface of the wall by radiation is given by this QR, that is Q radiation is equal to 1 into alpha, I into alpha, where I is the total radiation intensity and alpha is the absorptivity of the surface. Therefore, the total heat received by the outside surface of the wall can calculate with this formula. Therefore, the equivalent temperature T is equal to outside temperature plus the total radiation intensity into the alpha, that is absorptivity of surface by the outside film temperature, where the T is the solar air temperature. We have to calculate with this formula. Then the solar heat gain through the glass areas. This is one of the way the heat is entered into the conditioned space. And we have seen previously the solar air, and then heat gain, solar heat gain through the walls and roofs. Then the heat gain through the solar radiation. And like that, and through the walls, the heat gain through the walls. Then the heat gain through the glass area. The heat gain through the glass areas constitutes a major portion of the load on the cooling apparatus. When a sheet of glass is subjected to the solar radiation, a part of it is absorbed, a part is reflected, and the remainder is transmitted directly to the interior of the building. Generally, if you use the glass, maybe some amount of heat will transport into the inside room, and the glass may be sometimes and reflected also. That is the meaning of this. In the absorption portion, in the absorption process, the temperature of the glass increases until it is in a position to lose heat at the same rate in an interchange of energy with surface inside and outside of the building. A simultaneous interchange of radiant energy takes place between the exterior surface of the glass and the heated particles in the atmosphere, and between the interior surface and the various objects in the room. In addition to the radiant effects, the net heat gain into the interior of a building through a sheet of glass is affected by convection air currents on the both sides. If the temperature of the glass is higher than that of the outdoor air, there will be no gain by conduction in spite of the fact that the outdoor air is warmer than that of inside. In that case, the portion of the radiant absorbed by the glass will be removed by inside air currents. Another portion by outside air currents, and the remainder by the net loss in interchange of the radiant energy between the glass and all of the surfaces it can see. The complete heat balance can be written as follows. The net heat gain is transmitted solar radiant plus heat flow by convection and radiation heat exchanges between glass and the indoor surfaces. Neglecting the heat which may be stored in the glass or which may be given up by a glass under changing conditions, the second term of the above expression may be written as follows. Heat flow by convection and radiation of heat exchanges between the glass and the interior surfaces is equal to absorbed solar radiant plus or minus radiation and convection heat exchanges between the glass and outdoor surfaces. Then heat gain due to the infiltration. Already we discussed about the infiltration. The infiltration is air that enters a conditioned space through the window cracks and opening of doors. This is caused by pressure difference on the two sides of the windows and doors, and it depends upon the wind velocity and its direction, and the difference in densities due to the temperature differences between the inside and outside air. This is the, if any windows or maybe doors, maybe a small crack if it is there, then through that crack the air will be trying to enter the inside, because the outside temperature or outside pressure is more than the inside temperature and pressure. That's why through the cracks of the windows or the doors, the air tries to enter into that. And there are two methods of estimating the infiltrated air. One is the crack length method, the second one is the air change method. The crack length method usually used where greater accuracy is required. In most cases, the air changes method is used for calculating the quantity of infiltrated air. According to this method, the amount of infiltrated air through windows and walls is given by L into W into H into AC by 60 meter cube per minute, where this L is the total the room length in meters, W is the room width in meters, H is the room height in meters, and AC is the air change per hour. That means air change per hour means suppose if somebody has entered through the door, suddenly somebody wants to come inside the air conditioned room, he opens the door and then closes. And maybe second, one more person may be coming. That is the air change per hour. How many members are entering going out? That must have calculated in this case. The total room infiltration air and entire building is taken one out of the above calculated value, because infiltration takes place on the windows sides of buildings. The following table shows the number of air changes per hour for a variety of room types and exposures. These are the types, that is the rooms with no windows or outdoors. Maybe if there is no windows, means 0.5 to 0.75 number of air changes per hour we can take. And rooms with one wall exposure, that is per one it is 1, and rooms 2 walls 1.5, rooms 3 walls and 2, rooms of 4 walls and exposure, that is 2 times, the entrance halls 2 to 3, reception halls 2 times, 2 number of air changes per hour, then bathrooms, then 2 number. Like that way we can calculate the number of air changes per hour. For each person passing through a door leading to the outside or to an unconditioned space. The values given in the following table for the door infiltration should be added to the infiltration aid through windows and walls in order to find the total radiant infiltration. This is the usage of door frequently if you open and close, and at this time infiltration of air 1.8 meters revolving door in meter cube per person per passage, freely revolving door and a door equipped with brake. So like this way you can calculate the infiltration load. Then next one is the heat gain due to the ventilation. Already we have discussed the ventilation. The ventilation and the supply of outside air is provided the conditioned space in order to minimize odor, concentration of smoke, carbon dioxide and other undesirable gases so that freshness of air could be maintained. The quantity of outside air used for ventilation should provide at least 1 hour air changes per hour in buildings with normal ceiling heights. Also, if the infiltration or the infiltration air quantity is larger than the ventilation quantity, then the latter should be increased to be at least equal to the infiltration air. Outside air adds sensible as well as latent heat. The following table is there. The table, yeah. The following table shows the recommended and minimum values for the outside air required per person in the building. This is the table. Suppose if it's an apartment, then smoking area and outside air in meter cube per minute per person recommended is 0.6. Like that, that is banking space, and then barber shops, beauty parlor, cocktail bar, and like this way you can take the values depends upon the application also. Then the heat gain from the occupants, it is one of the heat calculations we have to consider. The human body in a cooled space constitutes cooling load of sensible heat and latent heat. The heat gain from the occupants is based on the average number of people that are expected to be present in the conditioned space. The heat load produced by each person depends upon the activity of the person. Already I told, and what type of activity is doing in the room. Figure shows a wide range of activities from the rest position to the rest position to one of heavy work. Yeah. This is the type of activity. It means the occupational degree of activity, typical application, total heat, adults, male, total heat adjusted, and then the sensible. Sensible is connected, and this is the seated at rest. Suppose if you are simply sitting, theatre maintained, then the total it is 114 and the total get adjusted 97. Like that way, and seated very light work or maybe moderate activity, office work, standing, light work, walking slowly, walking seated, standing, walking slowly, centered work, light bench work, moderate dancing. See, the dancing is always more, and then walking 4.8 kilometers per hour, then it will be more heat will be generated. Like this, the occupancy load we can calculate in watts. These are the watts, 104 watts and 104 watts, 132 watts. See, if you are walking at 4.8 kilometers per hour, then more wattage will be generated. Then the heat gain from the appliances. The appliances means that whatever the inside the building, frequently used air conditioned space may be electrical, gas fired or steam heated. The following table gives the most of the commonly viewed appliances together with approximate values of the sensible heat and latent heat. These are the appliances, and this is the electrical load, this is the gas. Suppose that coffee boiler 2.5 liter, and the sensibility is 264 watts, and the latent heat is 264 watts. If it is a gas, then it's 396 watts, and latent heat is 103 watts. Like that, the appliances will generate some amount of heat. Then the heat gain from the products. The heat emitted from the products to be stored is very important in case of the cold storages. That load to be considered in the cold storages are divided into the following two groups. One is the chilling load above freezing, and second one is the freezing load. The chilling load above freezing is the product chilling load above freezing depends upon the mass of the products, mean specific heat of the product, entering product temperature, final product temperature, and the chilling time. Mathematically, the sealing load above freezing maybe it is mCp into delta T. Almost we know that m is the mass of the. Then the CPM is specific heat, and the T1 is the temperature difference. Like that, freezing load. The freezing load depends upon the mass of the product. It's the latent heat of freezing, HFE, that is the latent heat, enthalpy R, and the freezing time, that is the TM. Mathematically, the freezing load may be Q is equal to this mass of the mass and the latent heat into the temperature, freezing temperature. Like that way, you can calculate the chilling load above the freezing and freezing loads. Then the cooling load below the freezing. The cooling load below freezing depends upon the mass of product, mass, M, mean specific heat of the freezing product, actual storage temperature of the product, desired freezing temperature of the product, and the cooling time. Mathematically, this cooling load below the temperature can calculate this formula. And then the fourth one is the product reaction or separation heat. During the maturing of some food products in cold storages, reaction or respiration heat is evolved. This heat is given by this Q is equal to m into evolution of heat per kg of food per hour. The rate of heat production for the different types of food is given in the following table. Okay, the table is maybe the data is very loose. For the syllabus, the table is not required. The heat gain from the lighting equipments. Suppose in the room, what type of lights we are using, that we also have to count for calculating the cooling loads. The heat gained from the electrical lights depends upon the rating of the lights in watts, use of factor, and allowance factor. Mathematically, the gain from electrical lights is by Q is equal to total voltage of lights and use factor and into the allowance factor. The use of factor is the ratio of actual wattage in use of the installed wattage. Its value depends upon the type of use to which the room is put. In case of the residence, commercial stores and shops, its value is usually taken as unity, whereas for industrial workshops it is taken as 0.5. The allowance factor is generally used in case of fluorescent table tubes to allow for power used by the ballast. Its value usually taken as 1.2 because the fluorescent light will give the more heat compared to your ordinary light. That's why generally for the residence, commercial stores and other shops and industrial you can take the 0.5. Whereas for the fluorescent light, this value may be 1.25. It is more value. Then the heat gain from the power equipments, the power equipment such as fan, motor, or any other equipments of this type of also adds the heat in the air conditioned space. The power consumed by the air conditioning fan is converted into heat energy and implemented and imparted to the air. If the fan is located before the air condition, the heat energy must be added to the total heat or total load. If the fan is located after the air condition, the heat energy is added to the room's sensible heat load. The electric motors used to operate the conditioning equipment within the conditioned space adds at least a part of the heat equipment, heat equivalent of the power consumed to the cooling load. The heat gain from the electricity motor is given by Q is equal to power rating of the motor in kilowatts by motor efficiency into the load factor. The load factor is the fraction of the total load at which the motor is working. So this fans, we have a motor, that motor generally gives some heat. That's why consider the fans and in the rooms also. And if it is low wattage, nowadays we have energy efficient fans, something that type of fan will give lesser wattage. Then the heat gains to the ducts. The heat gain due to supply that depends upon the temperature of air in the duct and the temperature of the space surrounded by the duct. The heat gain through the duct, that is U is calculated by U regulation. This is U, that is overall heat transfer coefficient into the area of the duct, and the temperature difference, that is TA minus Ts, where TA is the ambient temperature of air and TA is the temperature supply of the air, the temperature of the air. When all of the duct is in the air conditioned space, then the heat gain is zero. That means that because the air is, these ducts may be, where when we are using means the ducts are using, if it is a centralized air conditioning system, then the plant is located somewhere outside the conditioned space, and through that, from that unit, we have to take the duct, maybe some length, maybe it is near outside the room, maybe it is insulated, the duct also. Then after that, it is entered into the room. That's why when all the ducts is in the air conditioned space, maybe the duct is passing through the inside room, then the heat gain is zero. The duct is located and unconditioned space, that is outside the room, there is a gain in heat because you have measured the heat takes place. In order to prevent the condensation and reduce duct heat gain, the duct must be insulated. The heat gain to supply duct is roughly taken as 5% of the room sensible heat. It means that if you are not provided the insulation to the duct, maybe you can see some other super specialty hospitals or maybe some big shopping malls, their total air conditioning plant is somewhere located outside the building, and from that outside space they have to take ducts, and the ducts are insulated. Even though it is insulated, they have to calculate, they have taken roughly the value is 5% sensible heat. The loss due to the supply air leakage is not easy to estimate because it depends upon the workmanship of duct construction and the length of run it has been found that the depth leakages are to be are of the order of 5 to 50%. The air leakage from the supply ducts results in the loss of cooling capacity unless the leakage takes place within the conditioned space. The following are the minimum recommended values of air leakage through the ducts. Long runs have to measure the 10%, and the medium runs, that means the length of the duct. Long run means the length from the outside the plant to the room. The medium run is 5%, and if it is very sharp, then no need of consider the delay, load, leakage. Then these are the some you have to consider before calculating the heat cooling loads. Then we get some problems when we solve. The conference room for seating 100% is to be maintained at 22 degrees variable temperature and 60% relative humidity. The outdoor conditions are 40 degrees centigrade bulb temperature and 27 degrees variable temperature. The various loads in the auditorium are as follows. Sensible heat and latent heat loads per person is 80 watts and 50 watts respectively. Lights and fans 1500 watts. Sensible heat gain to the glass, walls, ceilings, etc. is 1500 and 15,000 watts. The air infiltration is 20 meter cube per minute, and fresh air supply is 100 meter cube per minute. 2/3 of the recirculated room air is air, and 1/3 of fresh air are mixed before entering the cooling coil. The bypass factor of the coil is 0.1. Determine the operator's dew point, the grand total heat, and the effective room sensible effect. So this is a problem. And actually, the air here, 2/3 of recirculated room air. That means we are using the air conditioning in the room. There must be outlet air also from the room. That is, the outlet temperature of air is always less than the atmospheric temperature. Though it is somewhat less temperature, we can recirculate that air to the room again. And we have to clean it before entering the room. Some cleaners may be there. And through that again some amount of recirculated air also entered into that. And suppose if it is a hospital, depends upon the patient. Suppose so many patients are there, and somewhat in ICU tends to carry diseases like something, if it is a transmissible diseases, then we have to turn to that. That type of patient is there, and from that room, that outlet air will not recirculate again, because it is already, the patient is maybe it is because the patient is somewhat, this is very dangerous. That's why that air escaped to that person. We can't recirculate it. Otherwise, if it is a normal, suppose simply the conditioned space in the classroom, suppose, and maybe the students are visiting the class, simply the outlet temperature can visit. That is the meaning of the 2/3 of the recirculated from the room air and the 1/3 of the air, fresh air, outside air. So this is the problem. And I think you know the the chart, and this is the given data. The number of persons is 100, and the variable temperature 2.2 is 20 degrees centigrade. Then the relative humidity is 60%. And this is the given data, whatever this, and this is the diagram. Actually, this is the outside air, 40 is the fresh air, and this is the recirculated air. That is maybe 2/3 of the recirculated air, and these two are mixing in this, and then it is a cooling coil. To the cooling coil, the this is entered into the conditioned space. This temperature is 22 and the relative humidity is 60%. See, this temperature and this relative humidity is a human comfort temperature and human conditions these two are. Right? And the isolated temperature, that is 40 degrees DBT, and the WBT is that is wet bulb temperature 27 degrees. So with this data, so it is very easy to draw the diagram. If you know this diagram, then your psychometric chart is very easy to draw. Then come to the psychometric chart. And these are the steps how to follow. This is the psychometric chart. Already you know what is psychometric chart we have seen in the last two classes. And first point, how to draw. First of all, mark the outside condition of air. Generally, outside temperature is 40 degrees DBT. So then, in these 40 degrees, this is the 40 degrees level of temperature. Mark it and draw a small line, dotted line on the psychometric chart up to this straight line drawing. Then, WBT. I think you know the WBT, that wet bulb temperature, always it is noted on the saturation line. Maybe somewhere this is the point 27 degrees. And then you join this line, 40 degrees dry temperature, and this 20 degrees, 27 degrees WBT. Then look at the point. That is the point 1, where these two are coincide. That is point 1. Look at that point. That is the first point. Now, mark the inside conditions of the air in the room, that is 22 degrees DBT and the 60 degrees relative humidity. So this is the second point. 22 degrees level of temperature and the relative humidity line. I think this is the relative humidity line. This is the curve line. Already have seen in the previous classes detailed. This is the curve line. This is 60%. So this 60% line and this 22 degree DBT line, you coincide somewhere. These two are coincide this point. This is the point 2. Okay, point 1 is here and point 2 is here. Then you can draw the line point 1 to 2. Then next point. Hard point. Locate point A by drawing vertical and horizontal lines through the point 1 and 2 respectively. From the psychometric chart, you can find the specific volume of the air at point 1. Go to again this figure. Once you know the point 1 and 2, then if you draw this line will be enthalpy, and this is also at point 1 enthalpy H1, and this is at point 2 enthalpy H2, and then this is point 2 exactly. And if you draw the vertical line, horizontal line, where it is coincides to the dry bulb temperature, this is the point A. This at that point A, you can calculate the enthalpy at this point. This is the point A, and then you can find out the from this point. If small curved lines are there, then it is a room sensible heat that you can calculate. That is 0.79. So if you draw a straight line to this where it is coincide is 0.6. That is the regular temperature where it is, you can calculate the point, and you will see one by one analytically also. So first of all, you know how to find out point 1 and point 2 and point A. From the diagrammatic chart, we find specific volume of air, 0.1, that is 0.911 meter cube per kg of dry air, and the enthalpy is 85 joules per kg of dry air. At 0.1 and at 0.2 enthalpy is 27.5 kg per kg of dry air. And enthalpy at point A, that is 66 kilojoules per kg of dry air. And therefore, with that, you can calculate the mass of infiltrated air at point 1 is V1 by Vs1, that is 20 by 0.91. This is equal to 21.95 kg per minute. That is the infiltrated air, mass of infiltrated air, that is. Then sensible heat gain due to infiltration, this is M1 into the enthalpy at point A and enthalpy at point 2. Then we can calculate that 6.77 kilowatts. Then we divide by 60, then it becomes kilowatts value. The previous is M1 is calculated. It is 21.95 kg per minute. Then you can calculate in per 60, then or maybe divide, then you divide the value is 4.6 by 60. And the latent heat gain due to infiltration, and this is the formula again, because HA, that is first at point 1 we take the enthalpy value, and then this enthalpy of at point A, then we'll get the value 6.95 kilowatts. The sensible heat gain from the person, that is the Q, number of persons into the 100. It is given in data, that is 80%, 80 watts it is load and the heat, then into number of persons, then you will 8 kilowatts. The total latent heat gain from the person. So it is a Q into the number of persons, that is the latent heat the person will give 50 into 105 kilowatts. Total sensible heat gain in the room is room sensible heat. This is the sensible heat gain due to infiltration air, plus sensible heat gain from the person, plus sensible heat gain due to the lights and fans, sensible heat gain to glass, walls and ceiling fans, all put together. It will give the 44.77 kilowatts. And total latent heat gain in the room, that is a room latent heat, is a gain due to infiltration air plus latent heat gain from the person. This will be 11.95 kilowatts. And we know that the room sensible heat factor, it is room sensible heat by room sensible heat plus room latent heat. We have seen earlier previous classes this formula. Therefore, finally the room sensible heat factor you can get 0.79 and you can mark in the diagrammatic chart that point. This is where this point will get this point. This is the 0.79 in the help of formulas. Like that way, you can calculate the values. Now, mark this circulated value, calculated value 0.79 on the sensible heat factor scale as point A, and join with point B, which is the alignment circle, that is 26 degrees DBT and 50% RH, is shown in the figure previously diagram. So the point 2 and draw a line 2 to 5 parallel to the line AB. This line 2 to 5 is known as room sensible heat factor line. Since 2/3 of the recirculated air and 1/3 of the fresh air is mixed before entering the cooling coil, therefore mark the mixing point 3 on the line 1 to 2 such that this line 2 to 3 length is 2.1 into 1 by third. From the cyclometer chart, we find the arrival temperature at point 3 is 28 degrees. If you see the cyclometer chart, this is the D3. This is. So with this values we can calculate all the values with the help of the cyclometer chart. Let the operator's dew point, that is the coil, we know that the bypass factor is given, it is 0.1. With that bypass factor, there is a formula TD4 minus TD6 by TD3 minus TD6. In that, we know the already have seen this 20 TD3, 28 driver temperature, and by the error method, we find the TD4, that is the 11.5 degrees. 13.15 degrees centigrade, and TD6 is the 11.5 degrees centigrade. Therefore, the grand total heat, we know the outside total heat, that is 0.02 into V1 into the enthalpy difference. Therefore, it can be 15 kilowatts. Therefore, the grand total heat is room sensible heat plus latent heat plus outer total heat. Overall heat total heat, this is almost 71.72 kilowatts. Effective room sensible heat factor, join 0.6 with 0.2 and produce up to the sensible heat factor scale on the cyclometer chart. The line 62 is known as the effective sensible heat factor line, and its value is given as its value is given in the diagram. Effective room sensible heat factor line. This one. This is the effective room line. Then you can take the values with the help of the chart. So this is the way how to calculate the cyclometric. Then the next problem. This is the second problem. The following data relates an office air conditioning plant having the maximum seating capacity of 25 occupants, and then the remainder outside design conditions are 34 dBT and 28 degrees WBT, that is the bedroom temperature. Inside design conditions are 24 degrees centigrade and dBT and 50% relative humidity. Solar heat gain is 910 watts. Latent heat gain per occupant is 105 watts. Sensible heat gain per occupant is 90 watts. Latent heat load is 2300 watts. Sensible heat load from the sources, other sources is 11,630 watts. Infiltration load is 14 meter cube per minute. Assume 40% fresh air and 60% recirculated air through the evaporator coil, and the bypass factor of 0.15, and the dew point temperature of the coil and the capacity of the plant. So try and do at home. Otherwise, we'll see in the next class how to calculate. Same follow previous problem like 34 and 28, and you note it is a 0.1, and then the remaining is you can note on the cyclometer chart with 0.2 is 24 degrees dBT and 50% relative 0.2. Then you join these two, and accordingly, like the procedure same previous problem, and then we will see in the next class the remaining, and you try to do at home, and we will meet on the Friday. Thank you very much.